Hello, my name is Suraya binti Hassan and my matric number is S72518. Today, I would like to talk about vacuum thin film coating system. A vacuum coating system is a precision system used to apply very thin layers of material onto surface such as glasses, metal or plastic. The material to be coated is placed inside a sealed vacuum chamber where pumps remove most of the air and unwanted gases. This low air environment allows the coating material to travel smoothly from its source to the surface, forming even and high quality layer. As a result, the coating bonds well and has better purity and durability. In a vacuum coating system, pumping is divided into primary pumping and secondary pumping to achieve the required vacuum level. A rotary vane pump works on the principle of positive displacement. It consists of rotor mounted eccentrically inside a cylindrical housing with several sliding vanes fitted into slots in the rotor. As the rotor rotates, centrifugal force push the vanes outward so they can remain in contact with the inner walls of the housing. This creates sealed chamber of varying volume between the vanes, rotor, and pump casing. When a chamber passes the inlet port, its volume increases, drawing gas into the pump. As rotation continues, the chamber moves toward the outlet side, where its volume decreases, compressing a trapped gas. Once the gas pressure exceeds the atmospheric pressure, it is expelled through the exhaust valve. Compression and exhaust allows the rotary vane pump in efficiently remove gas and generates a vacuum. A turbomolecular pump is a high vacuum pump used to remove gas molecules from a chamber by transferring momentum to them using rapidly rotating blades. It consists of a rotor with a turbine-shaped blades and a stator with fixed blades. The operating principle of turbomolecular pump is based on the transfer of momentum from rapidly rotating rotor blades to gas molecules. When gas molecules collide with blades, they are temporarily absorbed and then released, gaining additional velocity from the blade motion. This added velocity is combined with the molecule's thermal speed, directing them toward the pump outlet. To prevent the transferred momentum from being lost due to intermolecular collision, the pump must operate under molecular flow conditions where the mean free path of the gas molecule is greater than the spacing between the blades. A diffusion pump is a secondary high vacuum pump that functions as a momentum transfer device using high-speed vapor jets to remove gas molecules from a system. The process begins by heating a specialized diffusion pump oil in a boiler at the base until it vaporizes. This vapor rises through a central jet assembly and is ejected downward through supersonic nozzle at speed that can reach Mach 1. Gas molecules from the vacuum chamber diffuse into these dense vapor streams where they are struck by the heavier oil molecules and driven toward the bottom of the pump. As the oil vapor hits the pump, water cools out the walls. It condenses back into the liquid and drains back into the boiler to repeat the cycle. The trapped gas molecules are released near the exhaust at an increased pressure, allowing a primary vacuum pump to remove it from the system. A cryopump is a secondary high vacuum entrapment pump that functions by capturing gas molecules on a surface cooled to extremely low temperatures. Unlike other pumps that exhaust gas out of a system, a cryopump acts like a gas trap using a two-stage cooling process to immobilize molecules. The first stage, cooled to approximately 65 K to 80 K, primarily captures water vapor and heavy hydrocarbon through cryocondensation. The second stage reaches temperature as low as 10 K to 20 K to freeze air components like nitrogen and oxygen, while lighter gases like hydrogen and helium are trapped via cryosorption onto porous material like activated charcoal. Because it stored gas internally, the pump eventually reaches a saturation point where it must undergo regeneration, a process of warming up the pump to release trapped gases so they can be removed by a primary vacuum pump. Vacuum coating systems are widely used in modern industries to apply very thin layers of material onto surfaces to improve performance and durability. In electronics, they are used to make microchips and display screens by adding conductive and insulative layers. In the optic and glass industry, vacuum coating is used to produce anti-reflective lenses and energy-saving glass such as low-E windows. Overall, vacuum coating systems play a crucial role across diverse industries by enhancing functionality, longevity, and efficiency of products.